speaker is Professor Koji Hashimoto at Osaka University. He's one of the organizers of this workshop, and he's going to talk about building bulk from Wilson loops.
Okay, thank you very much. First, I'd like to thank Kunyon and Sanjin and Yaonias for organizing everything. And it's very nice that almost all speakers ate up all the time of discussion. So we have many discussions here. And I actually changed the title of my talk from complexity to this title. And in fact, in my talk, I will mention good relevance to complexity. So hopefully this can contribute to complexity. But the title which I deleted is about the machine learning. I tried to use machine learning to actually count the complexity for given Hamiltonian and given state. And it's kind of ongoing work. I wanted to present the results, but it's not yet complete. So hopefully in the near future, I can report on it in another occasion. So let me talk about this building bulk problem. So as you all know, the goal of ADS-CFT is to understand how the quantum gravity spacetime emerges from lower dimensional quantum mechanical systems. And in particular, once you know that a higher dimensional spacetime emerges from the viewpoint of ADS-CFT, then of course you are interested in what is the metric of this higher dimensional spacetime. And so it's one of the serious issues in ADS-CFT, how to construct actually the bulk spacetime metric from boundary QFT. So schematically, so this is the picture. So suppose you are given QFT. So for example, QCD or SYK or whatever, your favorite QFT. Then if it allows bulk gravity description, then there should be a way to construct a bulk spacetime from this QFT. But note that in ordinary ADS-CFT, what you do is opposite. You start from some bulk classical gravity or quantum gravity spacetime, and then use ADS-CFT dictionary to calculate, for example, correlation functions in QFT. So normally we go from right to left. However, the importance of ADS-CFT is that we don't know what kind of QFT are categorized as holographic QFT and what QFTs are non-holographic QFT. So the distinction between these two quantum field theories, one has a gravity law, the other doesn't have a gravity law. The distinction is necessary to be defined. But so to answer such kind of a difficult question, we need a method to build bulk spacetime from given QFT data. So the goal of this talk is to provide one formula to build a spacetime, bulk spacetime metric from QFT data. Okay, so I divided my talk to 4 sections, but each section has just 1 or 2 slides, so it's a very short talk. So you can ask me anytime and interrupt me anytime. First, I will explain the methods which have been proposed so far by many people, how to construct bulk from QFT data. So in fact, there are many methods, and some methods may be better in some sense, but the other method may be better in other sense. So there are many criteria and what kind of physics in bulk you want to consider. Depending on that, there are many methods, and methods are working. And I'd like to compare from my viewpoint, personal viewpoint, how those methods are compared. Okay, then in section 2, I will present you my formulas. I have a formula for building bulk from Wilson loops. So Wilson loops are very easy object, and many people know that. In particular, people in other areas like HEP, PH, HEP, LAT. So those people like to use quark potentials and Wilson loops for Yang-Mills theories. So I think my formulas may have a good sense of that. And in section 3, I use my formulas to rebuild ADS as an example. And in section 4, I present a very simple theorem about the confinement. So starting with the confining Wilson loop expectation values, what kind of bulk can be built? So this is the answer to that question. Okay, so here is one check sheet of comparison of method for bulk construction. So on your left, I enumerated just 5 proposed bulk building methods. There should be other methods, but these 3 are in particular popular ones. And the last 2 are proposed by myself. So first, holographic renormalization and holographic entanglement entropy and correlators and ADS deep learning and the present work, Wilson loop. And these things have pros and cons, and there are many aspects for discussing the comparison between these methods. But here I just concentrate on just 2 viewpoints. So one point is no use of bulk equation of motion. So why I'm interested in this? So suppose you want to actually construct a bulk from nothing. Then you have just QFT data. Then maybe you need to assume something for the bulk. And for example, if you assume bulk Einstein equation, then that constrains a lot, right? So we hope that Einstein equation emerges out of the boundary QFT. So if you want that, then we shouldn't use the bulk equation of motion, right? And in these building method, some method uses bulk equation of motion. So we need some pre-knowledge about the bulk. And also the second viewpoint, which I'd like to propose, is the lattice input. And in ADS CFT, CFT is always strongly coupled. So if you want to build some QFT data, then you need some non-perturbative methods to evaluate physical observables. And one major way is, of course, lattice simulation. So for example, lattice QCD, lattice Yang-Mills. Using QFT put on a lattice, you can compute many things. So I want to make an input of QFT data available in lattice simulations. If I like to do that, then what kind of method actually can use or cannot use? This is the comparison. So let me go through these 5 things. So first, this renowned method of holographic renormalization. So this by DeHarrow, Sorokin, and Skenderis 20 years ago. This is a very popular and very well-known method. So what do you do? What you do is, so we suppose and assume the Einstein equation in the bulk, okay? Then the Einstein equation has many solutions. And among many solutions, if you specify the boundary energy momentum tensor expectation value, then that actually fixes the boundary condition. Then Einstein equation is solved, then the bulk spacetime metric can be obtained. So this is a rough sense of holographic renormalization. So in fact, so you expand the metric function in the bulk by the radial coordinate. We can say that it's z. So you Taylor expand the bulk metric by z. And then there are coefficients. And if we can determine the coefficients, then we say that bulk spacetime is determined, right? And there is a relation between expectation value of the boundary energy momentum tensor and those coefficients. So once you have this energy momentum tensor, then it can fix these coefficients by this holographic renormalization group. And then bulk spacetime is built. So this is very nice. And of course, energy momentum tensor can be evaluated on lattice. So you can use that as an input. However, a bad thing about this is that, in fact, you have to use Einstein equation. So Einstein equation is assumed here. So how about holographic entanglement entropy? This is also a renowned method. So Ryu and Takayanagi said that the entanglement entropy or the boundary theory is equivalent to the area of the surface, which is anchored to the boundary of this entanglement area. So using this correspondence, once entanglement entropy formula is given on the boundary QFT, then that actually is related to the bulk quantity. And in fact, by a very nice work by Armsley and Bilson in 2008, there is an inversion formula which actually can invert the holographic entanglement entropy to the bulk metric. And the good thing about this is that we don't need to use Einstein equation. Since this is a minimal surface in the bulk spacetime, so you just use this Ryu Takayanagi formula and the inversion trick of this formula to actually derive the bulk spacetime. However, unfortunately, there is no way to calculate entanglement entropy for Yammel's theory. So even if you use lattice theory, then for example, to compute entanglement entropy, you need to have a ground state wave function, and lattice cannot actually evaluate this. So even though this actually works very nice, lattice input is not available in the current technology. So how about the correlators? So to build the bulk spacetime, in fact, there are many papers try to build the bulk from the boundary correlators. So suppose you consider some boundary correlators, then if the correlator in real space-time has some divergence, then that defines the light cone. And this correlator is related to the bulk geodesics. And once you know the geodesics globally, then from that information, you can build the bulk spacetime metric. So again, there is a nice formula invented by Hamsley, and also Winnie Liu and Langamani argued that. So from the geodesic information of the bulk, you can build a bulk metric. But unfortunately, also for this, you need a real-time correlator at finite temperature for the boundary QFT. And that is very difficult for lattice. You know, at finite temperature, if you want to derive the real-time correlator, then it's very difficult. Euclidean correlators are good for lattice. However, real-time correlators is difficult. So there is no checkmark here. So how about these things? So ADS deep learning, which I proposed, actually use the bulk equation of motion. So you need to have some pre-knowledge. But the input data is some one-point function of chiral condensate. So it is easy to actually evaluate on the lattice. But you need equation of motion in the bulk. The current technology which I'd like to propose is the Wilson loop. So Wilson loop is actually a minimal surface in the bulk. So it has an information of the bulk metric. So this is very similar to the entanglement entropy, which is also a minimal surface. The good thing about Wilson loop is that it can be evaluated on the lattice. So in fact, we can use lattice data as a QFT input and then build the bulk spacetime. Okay. There are several issues about how to use this Wilson loop formula, so I'll come to that later. Okay, so let me explain my formula by 3 slides. So here I'll show you the very famous Maldesna and Surgeon Ray and E's 1998 result about Wilson loop. So here is a bulk spacetime. And suppose bulk metric is given like this. Eta is the radial coordinate of ADS. F is the temporal component of metric. G is the spatial component of the metric. And eta is infinity is the ADS boundary. So this is the bulk metric. And in the bulk metric, you put the Nambu-Goto string like this, and then you solve the equation of motion of Nambu-Goto string. the distance between these two endpoints is r, and this r is the separation of two quarks, quark and anti-quark. And computation result of the energy of this fundamental string gives you the quark potential, right? So this is a very popular construction. And here I just wrote the formulas. The energy is given by f and g metric function like this, and r is given by f and g like this. And here eta 0 is the parameter. So eta 0 is a so-called turning point. So if you change the quark anti-quark distance gradually, then string probes deep infrared. So this eta 0 goes towards the infrared. So so this eta 0 is some given value. Then if you fix this value, then R and also the energy can be computed. So in this way, once F and G metrics are given, then it computes E and R as a function of eta 0. So once you do this integration and then get explicit forms of energy and quark distance, then you eliminate eta 0 from this formula, and then you get quark potential, E over R. Okay. And this is for the quark potential, but quark potential is related to log of Wilson loop. And a Wilson loop can have another version, which is a spatial Wilson loop. In the spatial Wilson loop, this rectangular shape of Wilson loop is placed in space and space. So normally in quark potential, this is time and space, the Wilson normal temporal Wilson loop. But in addition, you can have a spatial Wilson loop, and from that you can define spatial quark potential. So this is another information. Since this is about space-space correlation, the formula for this ES of RS is given by replacing this F by the spatial component G. So it has very similar formulas. But anyway, this is the way you can get E of R from a given string frame bulk metric. And I want to invert this. So inverting means that once this quark potential is given, how you get this F and G. So there is a big difficulty here, you see. So first, you need to define eta 0 in some way to break this into two equations. And then using that eta 0, you need to disintegrate this integral. Then as a result, you can get F and G. Okay. And in fact, there is a way to invert this, and that is my talk. So here, I don't want to disturb you with many equations. So this is just a result, and the proof is written in my paper. So if you are interested in the details, then please look at it. So first, zero temperature case. Zero temperature means that in this frame, F is equal to G. So there is only one function which is unknown. So if you can fix F, then that's the end. So this is the protocol. So there are two steps. First, we assume that the quark potential E of R is given by lattice simulation. Then first you solve this differential equation. So you just differentiate E of R as a function of R, then define F0. And then you get R as a function of F0 by solving this equation. Okay. And in fact, this F0 is nothing but this F of eta 0. So in this way, you can invert this first step. And second, substitute this R as a function of F0 into this differential equation. So here, this is an integral of F0, and F is here. And the left-hand side is eta of F, which is differentiated with F. This is a differential equation for function eta as a function of F. So you solve this differential equation, and then you find explicit function of eta of F. Then inverting this, you'll find FO beta. So it sounds complicated, but this is explicit way of inverting this procedure. So once you have a quark potential, then you get bulk metric. And in fact, this strategy was invented by Wilson in 2008 as for entanglement entropy. And I borrowed all of those machinery and applied that to Wilson loop. Okay. And for finite temperature, there are two components, F and G. So it's complicated, but you can do it. I don't want to explain the details of the protocols, how to invert this expression, but you can do it. All you need is Wilson loop and spatial Wilson loop. These two data actually can fix F and G independently. Okay. So in section 3, I'll show you the zero temperature result and its use. So for example, let me plug in this data. The quark potential is given by Coulomb potential. So this is the case for any conformal field theory. In conformal field theory, everything is determined. So conformal field theory doesn't have any scale. So once you give R, that is the single scale, then this scale determines the form of this function. The dimension of this energy is 1. So the right-hand side needs to be dimension 1. So it should be 1 over R. So it should be Coulombic. So using this as an input and plug in this formula, plug in this input to this formula, then we can build this metric. The result is this. So FO beta is given by exponential function. And you see this is an ADS spacetime. So as we expected, from CFT data, we can build ADS spacetime by using this formula. So what about other power law potential? So for example, 1 over R to the power of n minus 1. So if n is 2, then it's CFT. But if n is not 2, then this is not CFT. And in fact, if you plug in this as an input to the formula, which I've shown you, then we can build the near horizon geometry of DP branes. The result is that f of eta is given by a certain power function. And this power law is well known for near horizon geometry of BPS DP branes. So in this way, the simple examples of power law quark potential can build the bulk spacetime. Okay, this is the final slide. So suppose I start with a confining potential. So E of R is given by a linear potential. So that is confinement. Then what happens? I can show the following theorem stating that starting from confinement, the bulk geometry which is built from this formula with the confinement input always has an infrared bottom. As you all know, so-called confining geometry has an infrared wall. And that means confinement, we all know. But is it always the case to have the infrared bottom for the geometry when we have a confinement? That is the question. So in fact, 1998, Kina, Schreiber, and Sonnenschein showed that once the geometry has an infrared bottom, then with the computation of Wilson, holographic Wilson loop, it always shows a confinement. So this was given. So given a bulk spacetime, Wilson loop can be computed. So I want to go backwards. So given confinement, what is a geometry? And here the theorem shows that actually there is always an infrared bottom. So that is the content of the theorem. So let me go into a little bit more detail of this theorem. So here we assume the linear confinement. Linear confinement means that quark potential has a linear growth with respect to the quark distance. So sigma is a non-zero positive constant, which is the confining string tension. And of course, this is not growing forever. If you go to shorter distances, then it deviates from the linear behavior. And this deviation is parameterized as this power law function. And when the co-distance r is large, then it goes to 0. Okay. And the coefficient c is normally positive in any lattice simulations. So we assume this as an input. Then we use this and plug this into my formula. Then at the 0 temperature, we get the following statement. The built geometry has an infrared bottom. This f of beta, the bulk metric, approaches to a minimum value, which is non-zero and positive, at which the gradient of f with respect to the bulk radial coordinate eta vanishes. So it is a bottom of the geometry. And the location of the infrared bottom in this radial coordinate eta is at the finite value of eta when this n is larger than 2. N is here, the parameter. And it is at eta is minus infinite when n is greater than 0 but less than or equal to 2. So depending on how it approaches to the linear potential, the location of the infrared bottom may differ. However, in any case, there should exist an infrared bottom, and that's the content of this theorem. Okay, so this is the end of my talk. So it's almost 27 minutes. So I compared various methods about bulk building methods in ADS-CFT. And I prefer some methods which doesn't use Einstein equation, but which can use lattice input. And using these two inputs, so using this, so as for these preferences, I think my formulas may have a good situation. And these formulas it looks complicated, but it's explicit. So you can just plug in and compute and solve the differential equations, and that's it. And the ADS spacetime can be rebuilt by easy steps. And also, I also have a confinement theorem. So let me end with 3 things to discuss. So first question is falsification of gravity dual. So suppose I have some QFT or quantum mechanics or anything, then I ask, okay, this one has a gravity dual or not? Then the only way we can do is as follows. So first, using my formula, I built the space-time metric. And using this space-time metric and use ADS-CFT dictionary, we compute other observables in the QFT. Then you compare this QFT observables with some lattice simulations of the original QFT. If they differ, then I think this falsifies the gravity dual, right? So in this way, there is always a need of going backward to the bulk building and then comes back to compare whether this makes sense or not. Okay. The second part is the Lucia term. In lattice simulation, a core potential always has a Lucia term, which is due to the quantum fluctuation of string. And my formulas actually use only the classical gravity description and does not include the quantum fluctuation of the Namu-Goto string. So to compare that with the a real lattice QCD data of Wilson loop, we need some subtraction of Lucia term in Wilson loop. So this is a kind of issue for the use of Wilson loop. And thirdly, although I said that this method works for any space-time, including black hole, unfortunately, the temporal component F of the near horizon part of the black hole is very difficult to probe. The reason is that even though you put the probe Namu-Goto string to the bulk space-time, because of the black hole horizon, they break up. So my formula based on this connected to string may not work if the string is very close to the horizon. So in this sense, the very close part of this black hole geometry will be very difficult to probe from Wilson loop. There could be some argument on how to improve this kind of situation. But yeah, let me stop here since it's just 30 minutes. So I hope you enjoyed my discussion. Thank you very much.
Okay, thank you for your very interesting talk and perfect timing. So,
I'm an organizer, so.
Yeah, it's exactly 30 minutes. Okay, anyway, thank you. So any question or comments from audience?
Yeah, Koji.
Yeah.
Could you just repeat the claim of your the reconstruction of ADS and the confining geometry?
Confining geometry.
So could you just repeat the claim?
Yes, the claim is that so I use the quark potential as an input, and suppose this quark potential is confining. Confining means that the energy as a function of the inter-quark distance is linearly growing. So sigma is constant. So if you make a derivative, then it's constant. So this is an input. Then if I use my formula, then it says that the constructed metric f of eta has always an infrared bottom. That's the claim.
So inferior the bottom means you have some wall or...
Yes. Yes, so infrared bottom. The definition of infrared bottom is precisely as follows. So it goes to a minimum, and the minimal value is given by this confining string tension, at which the gradient vanishes. So for example, in pure ADS, f is given by exponential function, so it never vanishes, right? When it vanishes, the string and everything stops here. So there is the infrared bottom. Yeah.
Right. So I mean, let's simplify the argument by setting n Rn to the c is 0. So suppose it's just purely linear.
Purely linear.
Yeah. And then is there any, the definite form of f and g comes out?
No. So if I put this constant to be 0,
yes,
and if I consider only this one, then my formula doesn't work.
Doesn't work?
Doesn't work.
Surprising.
Yeah. So there should be always some part which deviates from this linear behavior. The reason is that in confining geometry,
it's not necessarily just power suppression. So.
Oh, that's right. That's right. So for example, I can replace this by exponential suppression.
Yes.
Yeah. In fact, this Witten's geometry can be reproduced by using the input with this exponential suppression. Yes. So, but I need this very small piece to for my formulas to work.
So also, could you repeat about the ADS reproducing?
Oh, yes. So in this slide, I explained two cases. The first one is this Coulomb potential as an input. Then from my formula, I get ADS spacetime. And the ADS radius L is given by this form, which is proportional to square root of C, where C is this coefficient. And in fact, in the case of n equal 4 super-Yang-Mills, for example, this C is square root of 't coupling constant. And if you plug that in here, then actually you reproduce the ADS radius of near horizon geometry.
Question would be, did you assume that the space-time dimension is, dx vector x is 3
No.
No. So so I see. So maybe it is not just what do you mean is not just the Coulomb, but 1 over R.
Yeah, you're right. So I just say that this is 1 over R, and in 3+1 dimension, this is Coulomb. Yeah. So for any CFT in any dimension, the core potential is 1 over R. Yes.
So in some sense, what you requested is just some scale invariance.
That's right. That's right.
This
and
T
then from yes.
Yeah, Wilson loop is a scale invariant. That was your solution. Okay. So that the ADS. So, all right, that makes sense. Yes.
Yes, that makes sense. Yes. Yes.
Okay, so any other question?
If there is no question, I have one comment about complexity.
Okay.
So as you see from the previous talk, for example, if you employ this CV conjecture, then CV conjecture means that complexity is given by the volume of the surface, which are anchored on different sides of extended ADS black hole geometry. So in fact, the whole the machinery which I presented here can be extended and generalized to the computation of complexity. And using that, so I'm currently working on it. But so suppose you can obtain C dot in QFT. C dot is the time derivative of complexity in quantum field theory. Then use that as a QFT data, and I can build interior of black hole spacetime from this formula. So I think it's interesting. Even the quantum field theory can build inside of the black hole by using this kind of an inversion formula. And once we can invert it, then we can discuss, for example, what is the Einstein equation in the bulk, for example. So this is just a built bulk. So this is a solution of some equation of motion. And we can discuss what is the equation of motion in the bulk, even inside of the black hole geometry. So relevance of complexity is that, but of course, everyone knows that it's difficult to even compute the complexity in the QFT side. So I'm not sure if it becomes a good input data of QFT or not, but anyway, once you get complexity as a data, then you can build inside of black hole spacetime. Yeah, that's a comment. Thanks.
Okay, so any other question?
I have one question, Hashimoto-san.
Yes.
So yeah. So my question. So in the original work of this Marudashina, this Wilson loop calculation has been done for this supersymmetric Wilson loop, and
oh, I see. Yes.
Yeah. So in theory, there are several kinds of Wilson loops, and as a result, different.
I see.
Well, do you have any choices for this?
So yeah, in fact, the original one is, as Take said, it's about supersymmetric Wilson loops. Yeah. And the supersymmetry broken, the SUSY broken, so non-BPS Wilson loops has been evaluated in the context of gluon scattering amplitudes in ADS-CFT. And the result seems to be a bit different. There is no concrete calculation of rectangular shaped non-BPS Wilson loop in N=4 super MLs, as far as I know. But I think the result would be different. So here I completely ignore the supersymmetry, as you see. So I'm not sure how. So precisely speaking, I think, yeah, supersymmetry condition may be consistently checked within these formulas, but I haven't worked it out. Yeah, so that's But thank you for the important points. I haven't addressed that points.
Yeah, I suppose some discussion was done by Polchinski between this supersymmetric Wilson loop and non-supersymmetric one. And it may tell us something.
I see.
And I have another question. And I couldn't get to the point of this finite temperature. In that case, so what was the claim in the conclusion section? Can you construct black hole geometry from this method?
Yeah, in fact, the answer is so yes and no. The reason is that metric has two components, F and G, right?
Yeah.
F is the temporal component, and G is the spatial component. And for G, I can construct this G from spatial Wilson loop completely. Of course, outside of the horizon. Yeah, I can build. But for this F, this you need a temporal Wilson loop, but temporal Wilson loop actually breaks like this. Right? So if the separation is small, then they are connected. But if the separation is big, bigger than the temperature scale, then it breaks. If it breaks, then there is no way to probe the geometry.
I see, but
so partially, so as for the G component, it's okay, but F component, partially it's difficult.
Suppose we consider Euclidean case, and then there is no inside, but still you cannot get any good information.
Sure. Yeah, in the Euclidean case, I think you can build everything. Yes.
Oh, so you mean in Euclidean case your method to work? So.
Yes. But in Lorentzian case, it breaks. Yeah, you are right.
I see. Thanks. Yeah.
Thank you very much.
Okay, so any other question?
I have one simple question. In this setup, what's the physical meaning of this extra dimension eta?
So physical meaning. What do you mean by physical meaning? So
usual interpretation is some renormalization group scale of boundary quantum field theory.
Oh, I see.
Through the bulk. But in this case, as far as I think it's not clear.
I see.
Because it some hidden internal length scale of the.
Yeah, that's right. So my assumption is that the metric is in this gauge where there is no eta component of the metric. So this is fixed to be 1. And so this is the proper distance measured in eta direction. So that's the definition of eta. But in the formulas of this Wilson loop, it appears as a function of F, for example. And F, I think, has a meaning of the energy scale. So for example, in this confinement theorem, the bulk metric function F at the bottom is given by the confining string tension sigma. So this means that the bottom scale is given by the string tension, the physical scale. And this physical scale is directly translated to this bulk metric function. So the meaning of this function is energy scale. And I think eta is some emergent space notion of the proper distance in the bulk.
I see.
Yeah, I have no more to say about that.
Okay. So any other question?
Sorry, I have a question about relation between your formula and formula by entanglement.
Oh, I see, yes.
So in 3-dimensional gravity case, so minimal surface's shape is similar to string.
That's right.
So then in 3D gravity case, is your formula related to formula by entanglement, or is it totally different from the formula?
So it's similar but different. The reason is that Wilson loop actually uses the time direction component, temporal component of the metric, but entanglement entropy does not use the temporal component of the metric because entanglement entropy is defined by Ryuta-Kayanagi surface in time slice of the geometry, right? So there is no need of a temporal component of the metric. And also entanglement entropy needs the internal space-time, right? So it is codimension 1 surface in this time slice. So Ryuta-Kayanagi surface actually covers all the internal space, right? So suppose you work with ADS 3 times S7 or something, then Ryuta-Kayanagi surface actually covers the S7 too. But in Wilson loop, we don't need the information about Wilson internal space. Yeah, so those are different.
So your formula doesn't depend on internal space.
Right. So Wilson loop is just a string, Nambu-Goto string, so it does not go into the internal space-time. So the formula look quite similar, but the content of the metric in that formula are different.
Thank you.
Thank you. Thank you.
Okay, so any other question?
Sorry, hello.
Yeah.
I have a short question similar to the previous one. I mean, in the beginning, you mentioned the no use of Einstein equations. So, but basically for this string, can we say that it's using the equation motion of the Nambu-Goto strings? So.
That's right. Yeah. So of course we need to assume Nambu-Goto equation of motion. That's right. Yeah. But Nambu-Goto string is just you see it's also used in lattice QCD. So when you derive Lucia term, then Nambu-Goto string is assumed to be a good approximation of a very long QCD string, and the bulk counterpart is naturally believed to be Nambu-Goto string again, but in a curved space-time. So you need to fix some probe and use that to probe the metric itself. And for example, in this ADS deep learning approach, we used bulk scalar field equation to probe the bulk metric. So scalar field equation is assumed, but Einstein equation is not assumed. So in this way, you assume some part of something which probe the bulk metric, and then from this information you build the bulk, and then after that you ask whether this bulk metric is a solution of Einstein equation. Yeah, that's a kind of strategy for entanglement too.
Thank you. But for the Wilson loop, for string equation motions, so what is the correspondence in the lattice side, or it's some, how to say, some assumption, or is there some correspondence in lattice point of view?
Would you repeat your question?
Sorry, yeah, I mean in the bulk we have the equation motion of the strings, and what is the correspondence in the lattice side? I mean,
lattice side is got exactly this quark potential. Yeah,
I see.
Yeah, so you place a quark and anti-quark, then you measure the force in between those two. So that is a lattice calculation.
I see. Yeah, that's it. Okay, thank you.
Thank you. Thank you.
Okay, so any more questions? Good. Again, perfect timing. You are the real organizer. You are controlling everything, including question and discussions.
Right.
Okay.
Thank you.
Let's thank Koji again for his interesting talk. Okay.